right? So welcome to the class about choice under uncertainty. As you can see, chapter 6 is being skipped. It's not gonna be in this class, right? If you want to read it, that's great. It's an interesting chapter about limited attention. In this class, we're just gonna skip it and we're gonna go directly to chapter 7. Choice under uncertainty. So I moved the location of this class from other years since COVID because we have to learn a little bit more about choice under uncertainty. Also, it's a very nice chapter to introduce a lot of things about behavioral econ, and then you can actually do a task about modeling. Okay, so you will be able to do that in the problem set this week. Okay, so the chapter otherwise is super simple. So here, we're gonna take even a deeper zoom to the problem of consumption, right? Instead of just studying any choice set as we studied before or studying consumption bundles, we're gonna study even an object that in some ways is simpler, but also has added complexities because we're gonna zoom in, as I said. So instead of studying simple commodity bundle as before, we're gonna study the following primitive. So consider some capital set, which is a set of final alternatives. In particular, in this class, you can think of set as being monetary prices, right? So this is basically a collection of monetary prices. It can be finite or infinite. For now, you can think it's finite, but then we're gonna basically extend it to infinite cases. Then we say P, again, notation Mascolet, not amazing, but this is where we're stuck. P is equal to set to R. And this is basically a mapping, right? That is gonna be a probability because it's gonna be always positive and it's gonna add up to 1. So we're gonna understand this as a probability. So a P is basically gonna describe a probability over money. So this is gonna be a lottery, right? So this is gonna be, P is gonna describe that for each monetary price, right? You can have a probability of earning this, right? Of winning this. So this is it. Now, formally, this is denoted by this triangle, which is called a simplex. The simplex of set is the set of probability distributions on set, right? And we say that P belongs to the simplex of set, okay? So this is a trick we're gonna use. So take any set of prices, set, so this, and then you make it a lottery, right? When you make it a lottery, you have this triangle thing, and this is called a simplex, right? So the simplex essentially has a property that any element here is always positive and it adds up to 1. That's the defining property of the simplex, okay? And we understand them as probabilities. Now, important thing, right? These probabilities, they are essentially like the lotteries in Ontario, right? So for instance, imagine what are the prices in the Lotto Max. So they have $0, right? With a big chunk of probability, right? 99.9. And then you have prices, like you say you have 1 million, 77 millions, whatever is up now. So this is a discrete set in this case, right? You have basically 4 monetary prices, 0, 1 million, 77 million, 100 million. And then basically you have a probability over that. And that's what you buy when you buy a Lotto Max, right? That's essentially a lottery. So a lottery is just that. Now, there are some important lotteries that we are going to use for our theory. For instance, the Dirac distribution. So these are the generic distribution that has probability 1 of a particular monetary thing, right? So this, for instance, I'm going to create a Lotto Max that never wins anything, right? It's just for charity. So you buy it, it's a ticket that never earns anything. So this is a probability 1 on 0 earnings. And that is, for instance, an example of a fictional Dirac delta. The notation is this delta of Z. So this put all mass, probability mass on the set. This is called a degenerate lottery. Now, for any 2 probabilities, P and Q, you take a number alpha and you can create compound lotteries. These compound lotteries essentially pay with alpha probability lottery P and alpha 1 minus alpha lottery Q. So essentially the way people think about it is like you have a coin, right? The coin can be biased, hence captured by alpha. If alpha is equal to 1/2, it's a fair coin. If alpha is different from 1/2, it's a biased coin. And the bias is captured by alpha. And hence, you flip the coin and then if it's heads, you pay P as lottery. And if tails, you know, you pay Q. Okay, so that is a compound lottery. Now, what is the choice structure here? So again, we have to have some sort of menus, right? Instead of linear budgets in this world, we have at this stage, which is more general, then we're gonna specialize it, is essentially just any subset of the simplex. So the simplex is the whole set of possible alternatives. And then what is a choice score? You're gonna have some menu out of the simplex, right? Okay. Now, so remember that here menus are of lotteries, not of monetary terms. So monetary prices are fixed, and then essentially you have menus of lotteries. So for instance, you can buy Lotto Max, and then you have another lottery, you know, as lottery number 2, right? And lottery number 3, and then, you know, maybe you can buy also in Vancouver. So you have a lottery from Vancouver, right? So you can imagine basically collection of lotteries as being the menus in this chapter. Now, again, same tricks as before, we propose a model of behavior. So what is a model of behavior? Is some preference relation, right? So we're gonna have some preference relation defined on the set of lotteries. So these preferences are defined over the lotteries, not necessarily over the money, okay? Right now, the primitive is just a preference relation over the simplex, okay? Mathematically, okay? So we're gonna compare Lotto Max 1 to Lotto Max 2. That's what we're gonna do, okay? Lotto Max versus Vancouver Lottery. That's what we're gonna do, okay? Now, so of course, we're gonna still assume complete and transitive preference because we're gonna keep the rationality assumption, okay? The only thing we're gonna change is that we're gonna now specialize rationality. So we're gonna make it a special case of rationality. And in particular, we're gonna introduce what is called expected utility representation. So we say a rational preference has an expected utility representation if there exists a Bernoulli, this name is just the name of a scientist, right? Utility function, which is denoted by small u. And this small u, it maps from monetary prices to money, right? So this tells you how much you like money, such that the function capital U of a lottery P is equal to what? To the summation over all possible monetary prices, Z over the big Z, capital Z, of the utility you get from the monetary price, small u of Z, times the probability of that monetary price, okay? So how do you recognize this object from IUS classes, right? So if you take essentially a random variable, right? And you did this operation, so imagine u is a random variable, right? Essentially what you're taking is the expectation of this utility, right? So here, what we're doing is taking the expectation of a function that is called u. So this can also be written, you know, as expectation of u, right?
Victor, I have a couple of questions. So yeah. First of all, what is exactly the difference between the set we're working with now, cell, with respect to X? I don't get, I mean, I think I understood.
So at this stage, right, X, remember, was a positive orthant, right? So it was a description of vectors, each of them telling you quantities of goods, right? Over from the previous chapter. Here, set can be that, of course. So you can also be putting lotteries over, for instance, commodity bundles. But right now, set is an abstract set, just describing potentially, and a leading example, monetary prices, right? For simplicity. But, you know, set right now is super abstract. We're kind of back to an abstract setup. And then, but we're not choosing over set directly. That's the key here. Instead, we're choosing over lotteries defined over set, okay? Like for instance, let me do a second example so we understand the difference. Imagine now set is the set of SUV cars, right, in London. And then tomorrow, you know, Western decides for charity to run lotteries over SUV cars, right? Okay, so they are basically creating a lottery over cars. And then they're gonna sell the tickets, right? So we're studying preference over the tickets, not over the cars, right? So the tickets with some probability that you win the car, okay?
So it's more general than X.
Yeah, so Z is more
X, but it includes okay.
Yeah, but here we have another layer, right? And this layer is the probability layer, right?
Okay, great.
Yeah.
Thanks.
Yeah, so again, why this is important? So of course, I'm describing gambling. You know, you can imagine quickly applications to finance. But also, you know, in general, all our life is full of uncertainty, right? Especially since COVID, even more. And in many cases, we have some probabilities, right? For instance, right now, you know, we know COVID very well. When we started, you know, the class, we didn't know COVID at all, right? Now we know it pretty well. So given, you know, vaccination, given the use of masks, are you indoors, outdoors, you know, age, you know what are your odds of getting COVID and basically also dying of COVID, right? So this is essentially anytime you take some action that is related to COVID, then you have some probability distribution, right? That describes the possible payoffs, okay? So SET, for instance, can capture that as well, right? Okay. So yeah, that's why this chapter is important, because essentially, like you can imagine, like in the COVID situation, nothing is for certain. That's the issue, right? As opposed to chapter 3, where you go and buy bread and butter, right? With certainty. Here, instead, you have to deal also with this additional layer of complexity, which is the presence of uncertainty and risk, right? So now, for instance, if you take 2 actions, each of them is associated with a probability. If you buy basically a lottery, this describes a set of probabilities over different payoffs, right? So you're basically buying lotteries. Okay, now what is important about this chapter is that instead of just studying a complete and transitive rational model, we're gonna take complete and transitivity given, and we're gonna add to it another property. And the additional property is gonna be that the preferences admit this expected utility representation. In particular, it's gonna say that I can evaluate lotteries using this model, which is called expected utility, which says that I have to know the utility on the set, right? Which is a traditional utility. And then I can average across the possible states, right? Or the possible prices, in this case set, by means of the probability that they happen, right? And this is gonna be a description of behavior. So this is a model I'm gonna study and try to see what are the implications and what are the pros and cons, and essentially at the end, the empirical implications and whether this is a good model or not a bad model. Now, full disclosure, why do we study this model? This model is the workhorse of all game theory, of all finance, of macro. So essentially, people are using this model since the beginning of econ. And a lot of people get confused that rationality for economists is expected utility, right? Just because it's so widespread, okay? But expected utility is essentially a model that takes this complexity of the uncertainty and make it simple by assuming that consumers deal with uncertainty in the following way. They take the utilities of the prices of Z, right, of the states, and then they average them according to the probability of each state or the possible set, right? Now, this is a model proposed first by von Neumann and Morgenstern when they were working on their zero-sum games prototype of the game theory, right? And has become so popular again because it's so tractable, right? It's a linear model of behavior. Now, what is important? I want you to realize something. So if I say in the previous chapter, what is the utility of perfect substitutes? So what is the key feature of a perfect substitutes utility function? So if you have, for instance, that it's additive, right? So it's additive. Okay, so the entries of the commodity bundles, right? They enter additively, right? Okay, and what's happening here in definition 43? So P here is the analogous of the X vector before, right? So now, how is entering P here? It's enter additively, right? So this, in a way, right, is a model of almost perfect substitutes. What this is saying, essentially, right, is that the probabilities of each of these events are independent of each other, right? So essentially, you know, this is assuming a world with the probability of winning, you know, $1 versus, in the example of the Lotto Max, 0 versus 1 versus 10 versus and so on, is described independently from each other, right? These are events that can be described in this additive way. Okay. So in particular, right, I'm also assuming that the probability here is not entering with any nonlinear term, right? So it's just a scale up by the utility of the money you want. Okay. So this model, in a way, you know, is, of course, has a special case, something that you all know, which is expected value. So let's go back to the lottery example. So what is a way to basically decide whether investing in a lottery is a good idea or not? So a classical thing you could compute is the expected value of the lottery, right? Agree? So is the expected value here a special case of this expected utility? Yes, because the U can be equated to the identity function, right? Hence, you can just put here, for instance, in this example 24, right? For instance, imagine that I have 1/2, and then my monetary prices are 10 and 0, right? So what will be the expected value of this? It will be 5, right? Now, this is essentially expected utility when the utility is just equal to the monetary price, right? So U of 10 is equal to 10, U of 0 is equal to 0. Do you agree? Now, is this the only way you can rank things? Not really. For instance, imagine I have a subject that has Cobb-Douglas non-expected utility to lotteries, such that the utility of this guy is equal to P1 to the alpha, P2 to the 1 minus alpha, right? As opposed to this, right, expected utility is essentially asking it to be linear, right? So 1/2 utility of 10 plus 1/2 utility of 0, okay? Now, so you can imagine that there are other ways people can rank, right, lotteries. But in this chapter, because of historical reasons, I'm gonna fix my attention to the expected utility case, okay? So everyone has any question here?
Yeah, so is there a possibility if you start with a nonlinear utility function such as this Cobb-Douglas to do a monotonic transformation in order to turn that into a linear utility function, or it's not possible?
It's not possible, right? So the only thing, if you do nonlinear transformations of a nonlinear object, the only thing you're gonna preserve is complete untransitivity, right? Expected utility property is going to be destroyed by any nonlinear transformation because the key defining property of expected utility is that it is linear, right? So any nonlinear transformation will break it down. So what I'm saying here, what I'm saying here is something simple. So until now, we have studied complete untransitive property inside a utility function that is completely nonlinear, right? And this thing can be preserved under nonlinear but monotone transformations, right? So for instance, you take the Cobb-Douglas and apply a logarithm to it, it's still the same preference, right? But if you start with a expected utility thing and put a log on top, then it's no longer expected utility, right? So expected utility is more fragile and it doesn't survive nonlinear transformation.
Yeah, I was like thinking of not applying the log to the expected utility, but the utility itself. Will it work in this case?
Yeah, so these transformations now do not make sense anymore because now expected utility becomes a cardinal object, right? So now the only kind of transformations you can make now are affine transformations. So you can scale them by a constant or translate them translated by a constant. You cannot do any more here.
But of course, I understand that in expected utility I cannot do that. But could I take this utility function, apply the log to the utility function, and then plug it in the expected utility or not?
No, that transformation basically means you're describing different preferences.
Okay.
Yeah. So here, you know, again, so preferences that are not rational, for instance, right? It can be things such as stochastic dominance. So this is another way you can rank lotteries. You can say, for instance, that if you compare two lotteries using their cumulative distribution, right? Then you can say that, for instance, one lottery is better than the other if one is first order stochastically dominant, right? That means that for any value y, the cumulative distribution of the first lottery is less than the other. That means that you always get more from one of them. So that's another way to rank lotteries, and that people use it a lot. But that's, for instance, not rational, right? In particular, it's not complete because you cannot rank every possible lotteries by means of first order stochastic dominance. So people in finance, they have lots of ways to compare lotteries, right? So for instance, the classical expected utility, you have variance, you have things such as stochastic dominance, you have lots of indexes, right? To try to have one summary statistic that tells you this is better than this other, right? Now, in reality, right, we're imagining now a model where you study basically all possible things that match this representation. That means there is some arbitrary utility over the monetary price, but it's just expected utility of that. So the probability of each state of the world multiplies each utility in each state of the world, and then you average over all possible states. Important thing about the notation, capital U is used here for describing the utilities over lotteries, and a small u is this utility defined over the set, right? So over the set of monetary prices. So you can think of a small u, this is called the Bernoulli, is utility over money for our leading example, while capital U is utility over lotteries, okay? And this is the expected utility in this chapter. Okay, now I told you that the expected utility, obviously, since it is a utility after all, has to be complete and transitive, right? Anytime you have a utility, you know this is one-to-one with complete and transitive, okay? But however, this thing is more than just complete and transitive. It's a little bit more, right? What extra property does this model has? The extra property is called the independence axiom. The independence axiom is an additional property on top of completeness and transitivity that says the following. Take three lotteries, P, Q, and R, and then take an alpha. Then if P is better than Q, this implies that for any combination alpha of P plus 1 minus alpha R, this is better than alpha of Q plus 1 minus alpha R. So what is the operation on the right? The operation on the right is the compound lottery that I described, right? Compound lottery between P and R is a better lottery than the compound lottery of Q and R for the fixed alpha, okay? And this happens as a consequence that P is better than Q. So remember the operation. So I have two lotteries, P is better than Q. Then I take P and compound it with R, right? R being an arbitrary thing. Then I take Q and compound it with R. And then I compare the compound lotteries of P and R and Q and R, and turns out that the ranking is preserved. Still, P is better than Q, okay? Do you understand the property? Now, this property, of course, what this is telling you, these guys, right, is telling you that if I change R to any lottery, right, this still will remain true. So still P will be better than Q. So let's say I replace R lottery by basically R prime. Will be the same true? Yes. So the compound lottery of P and R prime and Q and R prime will still be preserved such that the first lottery is better than the second, okay? What this is telling you, essentially, in this guys, right, is that we are requiring some form of linearity or substitution, right? So basically, you can take each of the entries of the lottery, right, and enter additively. So it's essentially a requirement of additivity, okay? This is what these independence properties do. Now, there is also a technical property I have to impose. Remember that in order to have utilities, you need to impose continuity, right? Here, we need to impose a stronger form of continuity. And this continuity is called mixture continuity. So for all P, Q, and R, if P is strictly better than Q and Q is strictly better than R, then the sets of numbers alpha, such that alpha P plus 1 minus alpha R is better than Q. So even combining P and R. Remember that R is below Q and P is above Q. If I combine P and R such that they still remain above, so alpha is a little bit tending more towards 1, right? Then this set of alphas that make this possible, and the set of alphas that make that Q is better than alpha P plus 1 minus alpha R, are open in 0, 1. So you can take all of this, replace the strict inequality with weak inequalities, and then replace all the open statements by closed statements. This is a geometric property. It's a topological property that will allow me to prove the existence of a utility. It's a technical condition, okay? So,
sorry, the alphas are different for one case and the other one, right?
So they have to hold simultaneously, right? So I know, yeah, for sure. This is, remember, Martin, the statement is all the alphas that satisfy this. So of course, the first set is different from the second set.
Okay, okay.
Yeah. And now each set just asks to be open. So essentially that. Now, again, mixture continuity. There are two ways to take it, right? So in a full class in decision theory for a second year class, then we go deep into mixture continuity, right? There is a problem set dealing with mixture continuity. For today's class, you know, it's important that you know that to guarantee technically the existence of a expected utility representation where the Bernoulli utility is continuous, then you need this condition to be technically sound, right? But at the same time, behaviorally, the condition that is required for expected utility is essentially independence axiom, right? So mixture continuity is something technical, but the fundamental property is independence, okay? Okay, now, so the independence axiom. So in all theory, right? So if I were teaching this 30 years ago, you know, the independence axiom, basically at this stage, I will try to convince you that it's a good axiom, right? There is some sort of normative appeal to it. So essentially this is saying that, okay, so we are adding to completeness and transitivity, which economists have agreed. There are properties that describe what we mean by rational agent, right? And then all of a sudden we're throwing another property, right? So it's not longer only rational, right? It's something else. It's rational with independence. So there is a last name to the rational name, right? So now you are something else. You are also independent. And at this stage, you know, one justification in the old times was saying, look, this axiom, you know, is actually something we should follow. So if I were choosing among lotteries, this should be something I could do if I am reasonable, okay? And you know the idea here is that somehow if you are evaluating lotteries, if you basically have are able to evaluate that P is better than R, and if you have the compound lottery with any third lottery, right, it shouldn't change your rankings because essentially you are kind of having an evaluation that should preserve the strong information that P better than Q gives you. Now. So there is a lot of work trying to justify in the old times why this is a good axiom, right? And the reason people did that back in the time was that because we didn't have data, right? So the only thing we could appeal was to the insights, right? So saying essentially that your brain should accept this is a good condition. And hence, if we decision theorists agree that humans should behave like this, then potentially humans, in fact, will behave like this. But of course, people have progress. Now we separate very clearly normative statements from positive statements. What are normative statements? Normative statements are what people should do, right? Normative positive statements are what people do. So my class takes a positive statement, a positive approach, right? So more modern scientific approach. So for instance, for me, I don't care if people should follow this versus other rule. I don't know what people should do, right? People do what they do, right? So I want to learn what people do in reality. So for me, this is a first guess that scientists, in particular, one of the geniuses of the 20th century, von Neumann, when dealing with econ and showing that econ is hard, came up with this cool idea of expected utility because it's tractable It is linear, hence you can do a lot of game theory with linear functions, right? Nice, but it doesn't mean, you know, it actually describes human behavior. And of course, the spoiler alert, I don't think it does, okay? So I think it's a cool model, it's a good approximation, but it's too simple, okay? So it may describe in very special situations, but in general, it's a bad model. So if, you know, if rationality were still not convinced of a bad model, even if more evidence are rising that is not ideal, expected utility for sure is one of the almost dead in the floor model, right? So that's one of the, you know, this is the easy target. So if you want to attack some form of rationality, expected utility, go for it. You're gonna find something against it, and it's obvious, right? It's a linear model, it's a vestige of a null time. It's very tractable and nice, but we don't need it anymore. Now, but why people still use it so much? You know, the strength of tradition, right? And also the strength of tractability. It's a little bit like why people use OLS, right? It's linear, right? Social science have shown us that again and again, the things are very nonlinear, but we still use these very rough linear approximations. Well, first of all, that's what stated us, right? So a lot of, you know, technological constraint there, but on top, right, it's just, you know, very hard to move boldly away the tradition, right? And the tradition is OLS. And here is the same. So a lot of game theorists do expect utility, not because they believe that it works, but because they were taught on this tradition, right? They know games with expected utility, right? Now, let's be clear now. I'm still now BSing. You shouldn't believe me. You know, there is a model. This model has been proposed. It's important for historical reasons. We hope it actually describes human behavior. We actually distill the additional property that it requires on top of completeness and transitivity. It is independence. Now we can test it, right? Potentially. And now we will know whether it's a good model or not. Okay, but before going there, let's do some nice theory. And let's do another classical representation theorem. So this is, you know, our first, you know, theoretical exercise before going to empirics. Yeah.
Very one question. So is there a new framework for uncertainty that is different from expected utility?
Yeah, so I mean, this is the famous Kahneman and Tversky prospect theory, right? So people are trying to, you know, I think this is one of the potential candidates that seems to do a good job. You know, prospect theory, I think, you know, is actually a pretty cool model. But, you know, I am also working on that subject. It's something that's still open. I think one thing that you can enhance expected utilities by allowing for inattention. So you can have sort of a modern version of expected utility allowing for an attention layer. But, you know, I think prospect theory is also an important part of that answer. That allows the non-linearities, and it's very powerful. But yeah, so people are working on what is the next expected utility, right? But in general, you can also say, you know, who cares about expected utility? Let's just do a non-linear utility. So I think that's another approach to it, right? So people use expected utility mainly out of necessity because they want tractability, not because you have to. It's just that if you are doing game theory, doing linear of utility functions was nice and allow you to have theorems, right? Now we don't need them in a way. We can just go and use a computer, right? But it's a balance, right? So you don't throw everything in the trash, right? So there are things that could be saved. But so the representation theorem, right? So we have to do this. This is kind of our warming up for then going to a little bit to the empirics and examples. But you know, we have to do a representation theorem. This is a micro class. The representation theorem is very similar to the original utility function representation theorem. Here, we are going to add more properties. So the rational preference relation satisfies the independence axiom and mixture continuity. Of course, here, all this chapter, we're assuming completeness and transitivity, right? So on top of completeness and transitivity, independence and mixture continuity, even only if there exists a Bernoulli utility, the small u, such that P is better than Q, even only if the expected utility of U is better than the expected utility of P is better than the expected utility of Q, right? As described by these summations. So what changes across these two statements? The U is the same, right? The only thing that changes is the lottery itself, right? So one is evaluated with respect to P, the other is evaluated with respect to Q. Any questions here?
Yes, sorry, one short question. So it is not possible to do a transformation of the Bernoulli utility, right?
Bernoulli utility, again, all these utility can be transformed by just a affine transformation. So any scaling up, for instance, you take the Bernoulli and scale it by 3, 4, any factor that is positive, right? And then any shifting. So you can take all these expected utility and add a 3 to it. So it wouldn't change the ordinal evaluations. Now, when the things you cannot do is any long linear transformation. So here, this object becomes cardinal, right? Now, the proof is a nice proof. This is one of the classical proofs of this class, and is essentially going to construct the utility from independence. And it's going to explain how independence actually pins down utility. So if the preference relation satisfies the independence axiom of mixture continuity, then there exists a linear function from the simplex to the reals that represent the preference. So note that this function here is just asked at this stage in this lemma to be a linear function. So in particular, you know, we are not requiring anything else besides being linear, okay? Now the proof is the following. So it's gonna have several steps. So bear with me, and it's gonna take most of the class, right? Find R1 and R2 in the simplex such that R1 is better than P and P is better than R2 for a fixed lottery P. Now to ensure R1 and R2 exist, we use continuity and finiteness of set, right? So this is just a technical step. Now the second step is to define the candidate lottery. Remember, there is always a step where I propose a candidate utility. This is the trick in this representation theorem. So what is the candidate utility here? A capital U of P is equal to alpha P being the constant such that it makes me indifferent between the fixed lottery P and R1 and R2. So this is a key experiment. So imagine an experiment, right? Where I fix any lottery P, right? So this is a fixed lottery. Now I take a best lottery and a worst lottery, right? And then I run the following experiment. I start asking you, look, what about if I give you a compound lottery, right? Alpha 1 of R1 and R2, 1 minus alpha of R2, right? This is question 1. Question 2 is instead of alpha 1, I give you alpha 2, right? Alpha 2 of lottery R1 and 1 minus alpha 2 of lottery R2. So in particular, for instance, imagine R1 is the best lottery and R2 is the worst lottery, right? So for instance, imagine that the fixed lottery is a half of a million, probability 1/2, and 0 of earning nothing, right? So with probability 1/2, you earn $1 million, well, you earn 0. Now imagine the best lottery is winning $1 million with probability 1, right? And the worst lottery is winning 0 with probability 1. Now the experiment I'm describing is telling you, now let's say I give you probability 90%, right, of earning R1 versus probability 10 of earning 0. Are you indifferent between that lottery and the 50% lottery? Obviously, you're not gonna be indifferent, right? So essentially, you're gonna start asking these alphas, right, the convex combination of R1 and R2 until you declare that you are as well with a fixed lottery P and whatever combination I'm giving you, right? And that's gonna tell me, right, in this experiment, right, essentially you're gonna stop at some alpha and you tell me that alpha, right? That alpha is gonna be the utility of that lottery, okay? The moment you're indifferent, I declare that to be the utility. Do you think it's a reasonable way to measure how much you like a lottery? It seems so, right? Essentially, it's giving you, measuring your probability of taking a gamble, right? And between a reference point, which is a max lottery, and a reference point, which is the low lottery, right? And essentially, the alpha lives between 0 and 1 and is measuring the intensity of how much you like the lottery, right? So when you are able to calibrate between the best and the worst, what makes you different with the P lottery? I declare that to be the valuation of the lottery, U of P. So now you understand what's going on, right? That's the main construction that we need. The rest of the proof is going to be essentially using that kind of construction to show that, in fact, it's a linear function, right? And to show that it represents the preference, right? There's step 1. So imagine P is better than Q, and then you have an alpha. between 0 and 1. And then you have that P is strictly better than alpha, the compound lottery alpha P plus 1 minus alpha Q. And this is better than Q. Okay. So essentially, you can take an alpha that satisfies this. This follows from the independence axiom. Note that essentially, if we have P better than Q, then alpha P plus 1 minus alpha Q is better than alpha Q plus 1 minus alpha Q. So this is just application of the independence axiom, right? So I'm just playing with the independence axiom. This will basically collapse to Q, the right-hand side, and the left-hand side will be left as is. Notice that by definition, P is better than alpha P plus 1 minus alpha Q. Now by transitivity, I combine them both, and I have that P is better than alpha P plus 1 minus alpha Q, and this is better than alpha than Q. So I'm just constructing, I'm just showing that essentially if I combine any two things, they're gonna live in the middle of P and Q. So this is the first step. Now the second step is the construction that I mentioned. So take P plus and P minus, P plus being the best lottery possible, and P minus being the worst lottery. This is essentially given by your preferences, right? So my preference, your preferences given by the symbol here are known to me. So according to those preferences, there is a max and a min, because this is, I'm assuming at this stage, this is a finite set. If that happens, essentially what I have is here the existence of a maximum and the existence of a minimum. As long as you are compact, even if you are not finite, you're fine. So you have existence of P plus. Now, P plus better than P for all P. And the worst lottery is that, of course, P for any P is better than P minus. Now, these two lotteries exist because, as I said, the preferences are transitive and complete, and the simplex is a compact set. And now alpha and beta, take any two numbers alpha beta between 0 and 1. Now I want to show the following. Take a beta combination of P plus and P minus, and take an alpha combination of P plus and P minus. Now, this compound lottery will be strictly better than the second compound lottery, even only if B is greater than alpha. So, of course, this is part of what we want to basically show. And you can basically show it very easily here by using our properties. But essentially, since P is better than Q, right? And by continuity, if I'm taking any B better than alpha, right? Essentially, you are going to have that this lottery is better than the second. Okay, now for any P, I want to show the following, right? And this is essentially the calibration part. That is the more insightful part of this proof. So there is a unique alpha P such that you can calibrate alpha P, P plus 1 minus alpha P, P minus. And this is indifferent to P. Existence is a consequence of mixture continuity. This is the only part that mixture continuity enters, right? So mixture continuity allows for this indifference part to exist. Now, note that P plus is better than P and this is better than P minus. Then the set alpha that such that the convex combination is above it, and the other set that puts it below are close. As I mentioned, mixture continuity, if I take all the strict preference relations and replace it by weak preference relations, changes the statements of the open sets to closed sets. So here I'm using closedness, right? So that means there is a sequence of alpha n's in intersections of these sets, right? That converge to alpha P, such that alpha P of P plus is 1 minus alpha P of P minus is indifferent to P. Now we know that a bounded sequence in a closed interval converges, so alpha P exists and is between 0 and 1 because it lives inside the interval that is closed. Uniqueness comes due to a step 2. So step 2 essentially shows that if this thing holds with the strict inequality, then it has to be even only if B is strictly greater than A. So uniqueness means that if there is another alpha P that also calibrates with indifference, right? And that alpha P prime is greater than alpha P, then the original utility has to be strictly greater. So it is not indifferent anymore. So that's approved by contradiction, right? So that means there has to be a unique alpha P that calibrates the utility. So far what I have done is that I have created a utility function, right? And this utility function represents the preferences, right? We're gonna show essentially right now that it does, right? So by step 3, we have that P and Q, any two lotteries here. And if I observe that P is better than Q, now take the calibrated utility. So alpha P of P plus 1 minus alpha P of P minus is greater than or equal than alpha Q P plus 1 minus Q P minus. And this holds even only if alpha P is greater than or equal to alpha Q. So essentially it means that if P is preferred to Q, alpha of P is greater than or equal to alpha of Q. So this means representation, right? So let's go back to the idea of the experiment. So if you have a lottery that is better than another, so if you are running this list experiment asking you to calibrate the first lottery with respect to the best to the worst according to an alpha, the alpha of the first lottery P is going to be a greater alpha than the lottery Q, because P better than Q means that you require more of the best lottery P plus in order to be indifferent to P than in order to be indifferent to Q, right? That's essentially what it is saying. And the final thing that is the key of the proof is that this utility, of course, is not just any utility. It has to be a linear utility. So we want to show in particular that if I take the compound lottery of beta P plus 1 minus beta Q, according to this constructed utility, this is equal to the same beta multiplied by the utility of P by 1 minus beta of the utility of Q. So as you can see, linearity means that if I take the compound lottery inside the argument, it will go outside, right? So now you have beta of U of P plus 1 minus beta of U of Q. Now, everyone understands what's linearity. Now let's show that in fact it holds here. So note that P is indifferent to what? So remember there is a P plus and a P minus. And what is the utility of this? Essentially, the utility of P is the compound lottery factor, right? So this is U of P plus 1 minus U of P. And Q, the same thing. Q is indifferent to U of Q, P plus 1 minus Q, P minus. Now, apply the independence axiom. So that means that if I take the convex combination of beta P plus with Q, right? This is gonna be indifferent to this whole object here, right? Which is just the lottery with P plus P minus calibrated with UP, right? Now with the compound lottery beta plus 1 minus beta of Q. So this is true because essentially I take the original definition, right? And now I'm taking the indifference, I'm taking the operation with the third lottery Q, and I'm doing this here, right? So this is not gonna change the difference relation between these two objects, okay? So P here is indifferent, of course, to this object here by definition. And then I'm doing a combination with an arbitrary lottery, in particular choosing Q. By the independence axiom, I know this means these two are indifferent, okay? Now, this is also indifferent to the following object, which is essentially the convex combination of this object here, right? Plus 1 minus beta, the convex combination of this object here with respect to Q. So essentially what I'm doing again is just applying the independence axiom again. And now I have rearranging terms. You can observe that the convex combination of beta plus 1 minus beta Q that I have here is indifferent to the expansion, right? Where I can essentially put everything to inside this factor. So rearranging the P plus terms together. And they have a factor beta U of P plus 1 minus beta U of Q, and 1 minus beta of U of P plus 1 minus beta U of Q, P minus. That means, right, that what is the expected utility or the utility capital U of this compound lottery is essentially beta of U of P plus 1 minus beta U of Q. So this is applying again and again independence axiom and just playing with rearranging terms. It just shows that the capital U I created is a linear function. Okay, so this is the lemma. So once we have established the lemma, the final step is a technical step that the proof is omitted because these are result from linear algebra. sometimes from functional analysis as well when it's in the infinite space. And the lemma says the following. If you have a utility over the simplex, right? And if the utility is linear, this happens if and only if there exists a small utility U such that the linear utility can be described as this inner product of this vector U and this vector P, okay? So in other words, any linear mapping can be described by means of an inner product with one of the components of the inner product being a constant number, which is this U. So in other words, this is called the Riet's representation theorem. And this is a non-resolving linear algebra and in functional analysis that guarantees that any linear mapping can be described by an inner product. Okay, and the inner product is up to a constant. And this constant vector is here. We call it the Bernoulli utility. Okay, so the key part of the proof is this linearity part. Okay, this part here is a technical part, and this guarantees the existence of the Bernoulli utility. So important take-home message here is that the independence axiom allows us to basically have cardinal meaning to the utility, right? If you knew the values of the P plus and the P minus, and you normalize the utility of the P plus to be 1, and the utility of P minus to be 0, right? Then actually the value of the alpha P associated to any P lottery is a cardinal value associated to what you derive from consuming P, okay? So this expected utility number is a cardinal object, okay? And in fact, the way you get it is by this least experiment I described, okay? Any questions here? Okay.
I have one general one. Going back to the beginning of the lecture, I think about the simplex. We can use any probability distribution at all. Is that right? So it doesn't necessarily have to be Bernoulli. It could be whatever we come up with.
Yeah, so here, be careful with the name. So Bernoulli is not about the Bernoulli distribution. Bernoulli is the name of the small utility. So it's just a historical reason, right? So okay. Bernoullis, there were many brothers, right? And some of them were economists, others were statisticians. So this is about the Bernoulli related to econ. So this Bernoulli guy is essentially one that said, look, we can use utility functions instead of just having the expected value. So instead we can just put, for instance, a utility function. And I'm going to give you an example in a second, right? But for instance, one example of a Bernoulli, classical one. So imagine, for instance, they have a certain lottery, right? You have two possible prices. And you have, for instance, the following, the probabilities over that, right? One example being probability of 0 is equal to 1/2, right? Probability of 10 is equal to 1/2. Right? And now when you type this thing, right? For instance, you can have 1/2 of the utility of 10 plus 1/2 of the utility of 0, right? Now, in particular, I can choose the Bernoulli utility to be to the factor of sigma, for instance, right? So that's a classical one. Another would be, for instance, log of 10, which is another classical one, right? So this is a particular Bernoulli. So the Bernoulli is essentially some function, right? Doesn't have any restriction right now that puts the value of money. So how much do you value money in this particular case? But I can have way more complex examples, right? Now, let's finish the representation term, right? And it says the capital U represents the preferences and also U prime. So you have now two utilities that represent the same preferences. Now, then if that happens, there exists real numbers alpha, positive, and B, any real number, such that U prime of P is equal to alpha U of P plus P for all P. So that means that if U and B are Bernoulli utilities such that U times P, this is inner product notation, and B times P represents the preference, then there are real numbers alpha and B such that B times P is equal to alpha U times P plus P. So this is using the inner product notation as well, but you can see it's the same object. Importantly, right? And these are a lot of questions by Martin. So here, nonlinear transformations are not allowed anymore. The only transformations that preserves the expected utility framework and information are affine transformations, right? And in particular, positive affine transformations, because the alpha has to be strictly positive, okay? So if you can scale up the Bernoullis by any alpha, for instance, I can put here a 4, right? In particular, any kappa constant, right? As long as kappa is positive, then this is still the same preferences that I described before, right? So by scaling kappa by 10, by 100, is still the same preferences, right? And they are expected utility. Okay? So that means up to scale and location. So when I'm saying these are cardinal, they are cardinal up to 2 factors, right? So in particular, in order to know the actual number of the utility, you have to normalize the utility of the best object to a value, for instance, 1, and the utility of the worst lottery to another value, for instance, 0, okay? And if you do that, then essentially the utility number you get is a normalized utility, expected utility, and this corresponds to actually cardinal value of how much you like this lottery. So in the world of expected utility, you can actually have cardinal utils, right? So actual people can measure exactly how much you like things, if you happen to be in expected utility. Okay, so let's go with this because it's important. So attitudes towards risk. Okay, so why do we have this model? This model is tractable. Now, is this model still useful? Well, yes. You can basically use the Bernoulli utility and put restrictions on the Bernoulli utility to capture attitudes towards risk. One thing we'd like to know, whether people like to gamble, right? So they like risk or they hate to gamble, right? They hate risk. In particular, we have certain names that we're going to introduce, but we're going to use some definitions before. So expected value certainty equivalent. So we say a Dirac delta. So remember this, that the degenerate lottery that pays set is expected value certainty equivalent of P if set is equal to the expected value of the lottery. So this is a lottery that pays with probability 1, the expected value of the lottery, right? So take a lottery, for instance, the previous one, in the example, what is the expected value of this lottery according to this probability? So it's going to be 5, right? So if I create a lottery that pays with probability 1, $5, this is the expected value certainty equivalent, okay? Now, a decision maker is risk averter if and only if for any expected utility certainty equivalent of P, the expected certainty equivalent is preferred to the P, okay? So in other words, these people like certainty a lot, right? So they have to be risk averters. So the risk aversion is high, okay? So they prefer a certain expected value instead of the price. So for instance, imagine you go back to this lottery here, and then they tell you, look, with probability 1, you're gonna earn $5, right? So that lottery has to be better than this particular lottery of winning with probability half $10 and with probability half 0, okay? So a risk averter clearly will take the certain object, right? Give me the $5 now, okay? Instead of running the lottery. Do you agree? So that's a risk averter, okay? So this definition is nice in a way because it doesn't require anything about the even expected utility. So it gives you kind of a broad definition of what it means to be risk averter. Now, under expected utility framework, this actually has a very special meaning. It just means that if you are risk averter, it means that the Bernoulli utility, small u, is concave. And this is a consequence of the famous Jensen's inequality, okay? So Jensen's inequality essentially will tell you that the expected utility is less than equal than the utility of the expectation, right? If the U is concave, okay? And if the U is convex, it will be the opposite, right? So now, if U is concave, you're a risk averter in the sense we described. If U is convex, you're a risk lover, okay? Do you understand? So that's the nice thing about this expected utility model. It's for good reason people use it, right? It's not only that it's simple and linear, it also allows you to describe attitudes towards risk just by changing the shape of the small U. So it's good for modeling, right? Now the proof is again a simple application of Jensen's. Here, you know, this part I'm going to skip. You can read. These are additional definitions of risk uncertainty using different objects like the probability premium and the certainty equivalent, right? So you can check it yourselves. And then this proposition essentially says that decision maker is risk averse, U is concave, and then this probability premium and expected certainty equivalent have to follow certain inequalities. So read that part. This is just for you can read other literature as you go through your career. But here, you know, it's not very essential, it's very simple, and we didn't do the proof. What I want to do now in the last minutes is that all this theory we developed, we can also extend it very easily to infinite setups. So why do we want infinite setups? So in particular, we know that if you're doing finance, this set can be very large, right? So it can be very complex contracts, very complex baskets. So in particular, you now want to put probability over these sets, it's going to get more complex. So we need to introduce here the concept of sigma algebra, right? You have seen also with Nail. So in particular, a sigma algebra is just a collection of subsets from the power set, and they have three properties. The empty set belongs to the sigma algebra. Even set E belongs to the sigma algebra. The complement E also belongs to the sigma algebra. And importantly, if you have a collection AN is a countable collection of sets, such that each AN belongs to the sigma algebra, then the countable union of this collection of sets is also in the sigma algebra. So the sigma algebra is the main defining property, is that it's closed under countable unions, okay? Now, we say that this space is measurable whenever this sigma is a sigma algebra. And we say P is defined now a probability over the sigma algebras, is a probability measure. If P of Z is equal to 1, and then of course in countable events, the probability of the union of the countable events is equal to the summation over the probabilities of these events. Now, this just is clean the house to allow to have probabilities on infinite sets. You know that you cannot just put probabilities on some sets. Some sets are not measurable, right? So we are just allowing to have a measurable space. Some spaces are not measurable. So we're just doing the house cleaning in order to have a probability defined. Once you have a probability defined, essentially you again just require independence. And in particular, in this more general setup, we need a different form of continuity. And this is called weak start topology. And then essentially, this weak start topology uses expectations. And we fix a topology in the following sense. So Pn converges in the weak start topology to Q if for any family of integrals for any bounded function f, this family of integrals converges to the integral f of dp. So this is called a weak start topology. You want to dig out, if you know more math, this is very nice. You can go deeper into this. For the rest, what you want to understand is we're keeping the soundness of the proofs, right? This is a particular topology in the space of lotteries now defined over infinite spaces. So this is the correct way to do it. In particular, you are just using integrals and we're defining the convergence by means of integrals with respect to any bounded function f, right? So now using the weak start topology continuity, it says the following. You have the sets of upper contour set of P and lower contour set of P, and those are open in the weak start topology. Again, if I take the strict preference and replace it by weak preference, this will become now closed sets. So remember what was the notion of continuity in preferences in the chapter 3? It was that the upper contour set was a closed set, right? We're back to that. We just have changed topology. And now the theorem that is stated without proof, because the proof is too technical for this level of the class, is that a rational preference relation on the simplex satisfies independent axiom and weak star topology, even only if there exists a U, null utility mapping from set possibly infinite to reals, bounded and continuous, such that the capital U, which is now an integral of the U of Z with respect to the measure P, so D of PZ. So examples of this, and then there's going to be an application that you can read on your own. The only thing, so here I'm stopping. You will have to read the Alais paradox. We're going to cover it also again in the next class. But your problem set is going to be about the Alais paradox. So the Alais paradox essentially is going to tell you that there are certain behaviors that we see in data that do not fit the expected utility. And that's why it's called a paradox. So Alais, he's a researcher, was a researcher, I think he's that. And he essentially was proposing an example of behavior that goes against expected utility. So you will have to read this and then essentially propose a model in the lines. Is very guided problem set where I'm going to tell you in these lines, try to propose a model alternative to expected utility that explains the behavior, right? So it's not going to be a model out of the blue, but rather a modification of expected utility, allowing for some non-linearities, okay? So you will see the problem set when I release it today or tomorrow in the morning, okay? So this is the class for today. I'm going to stop recording.